Section 5.3, inverse functions. We're going to take a look today at inverse functions in general, and then as we move in further into this chapter, we will see how the logs that we just did in sections 1 and 2 interplay with this particular section. So to start with, a function g is an inverse of f if f composed g of x is equal to x for each x in the domain of g, and g composed f of x is equal to x for every x in the domain of f. So you've done these kinds of problems before. Again, this is a concept that you first are introduced to in a college algebra or maybe even an algebra 2 or a math analysis type course. The function g is noted f with the little negative, looks almost like a subscript or a superscript, right? Which is read as f inverse. So that little negative 1 up there is read as f inverse. All right, so we're going to do an example of what you would have seen prior to now, kind of like how we've started the last two sections, with inverses. So f of x is 5x plus 1, and g of x is x minus 1 over 5. And what we're going to do is we're going to show that they are inverses analytically. So analytically means that we're going to actually do these two operations. We're going to do f compose g of x, and we're going to do g compose f of x. Okay? So some of this you might remember, and some of it you might be like, that sort of looks familiar. We're going to do f compose g of x. My screen is not wanting to write very clearly today. All right, so our f of x function, written right here, is 5x plus 1. So what this notation is telling you, if you'll remember, is that g of x, which is this quantity right here, needs to go in the place of where x is in the f of x equation. So we're going to write down the 5, but instead of x, we're going to write down x minus 1 over 5. That's in place of the x. And then we're going to do plus 1, because that's part of the original f of x equation. And our goal when we simplify it is that if this really is an inverse, we should end up with x when we're done. All right, so very clearly, what do you see simplify?
The 5 and the 5 are going to cancel.
Right, the 5 and the 5 are going to cancel. And then we're going to end up with x minus 1 plus 1, so the 1s are going to cancel, right? So this does, in fact, equal x. Agreed? Now, that's only half of the question, though. You have to do it both directions. Not that the other direction's any more difficult, but sometimes weird things happen in one direction that don't in the other. So now we're going to do it the opposite way. We're going to take everything that f of x is, which is the 5x plus 1, and we're going to plug it in place of the x in the g of x equation. So instead of x, we're going to have 5x plus 1. And then we're going to have minus the 1 and divided by 5. So what would actually simplify first on this one? Yeah, the adding and the subtracting of the 1s. And then you'd see the 5s also simplify second. And again, you would end up with x when you're done. Okay? Now, this is a pretty simple description of one, right? These were simple linear equations. These are both linear equations, actually. So they're a little messier if you have radicals involved, or if you have exponents that are, if you have equations that are not linear, so like x squareds or square roots involved, those kinds of things, they become messier pretty quickly. But the process is still the same. You compose them this way. Now, what we're going to show, and I want to remind you of graphically, is what it means, or what it means graphically for them to be inverses. So take your calculator, and I want you to put each of these inside of your calculator. And like I mentioned, they're both going to be lines, so this is not going to be a very exciting graph, okay? All right, so we have 5x plus 1 in one screen, or one equation. The other one should have x minus 1 in parentheses, making sure it's on top, divided by 5. And if you do a standard 10 by 10 window, you get a graph that looks something like, let me draw what mine looks like, and hopefully yours does too, since I don't have my calculator screen. How's that? Is that what your graph looks like? Excellent. That's what it should look like, roughly. And if you were to label them carefully, you would find out that this was the first equation you graphed, f of x, and this was the second one, g of x. What I want to show you is what this means graphically. So for functions to actually be inverses graphically, it means that they are reflections of one another along the line y equal x. So the line y equal x here is right here. Well, let me try that one more time. That's pretty good. And can you see the reflection that you're getting across that line? Now, it's pretty easy to see with lines. Sometimes it's more difficult with some other graphs that we draw. So if you drew a square root graph and you saw that one wouldn't be too bad. But the more going on in the graph, the harder it is to see the reflection in them. But they are, if they're inverses, going to be reflections over the line y equal x. All right, so if this is what inverses sort of do for one another, they have these characteristics or these features, how do we know if something has an inverse? Well, the first issue is we have to know if something is one-to-one. So a graph is one-to-one when it's a function for which every y value corresponds to a unique x value. That is, if f of a equals f of b, then a equals b. Okay, so for every y value that's the same, the x value has to be the same if a graph is one-to-one. Now, what this really says in a positive light instead of a negative light is it's saying I can't have two y values that correspond to two x values. So something like a parabola in its entirety doesn't work because it duplicates a lot of the y values, right? So you have two y values maybe at a height of 7 because you have the y value 7, you have two x values, maybe it's at 3 and it's at -3, okay? So that can't happen if a graph is one-to-one. And the easiest way to test for that is something called the horizontal line test. The horizontal line test, I said it right. The vertical line test is what you used back in the day to decide if something was a function, right? If you do a vertical line test and it crosses the graph in more than one place, not a function. Same thing for the horizontal line test. If you do the horizontal line test and it crosses in more than one place, it's not one-to-one. And if it's not one-to-one, then it doesn't have an inverse. That's the kicker. Okay, it's got to be one-to-one. So a graph is called strictly monotonic if it is strictly increasing or strictly decreasing on its entire domain. Okay, so it's always increasing or it's always decreasing. And you know plenty of graphs that do this and plenty of graphs that don't. So I'll give you an example of a graph that doesn't. A parabola, right? Sometimes it's increasing and sometimes it's decreasing. In fact, it's about 50-50. I mean, that's the whole point. It's a symmetric kind of graph. So that would not be strictly monotonic, right? All right, but you do know one that is strictly monotonic. It's one that we just encountered in the last two sections, logarithmic functions, right? Log functions are strictly monotonic. The y equals ln x is a strictly increasing function. So this one I already alluded to. A function will have an inverse if and only if it's one-to-one. So a parabola on the entire domain is not going to have an inverse. However, if you restrict the domain, like you only say x is greater than 7, or something like that, where on that piece of the graph it's one-to-one, then you can talk about its inverse. But it doesn't have an inverse if you talk about a whole parabola. And if f is strictly monotonic, I guess I got the f left off here. Let's put that in. If f is strictly monotonic on its entire domain, then it is one-to-one and therefore has an inverse function. So this relates the graph's feature of it being increasing to its ability to be one-to-one. So strictly increasing or strictly decreasing, you definitely have something that's going to be one-to-one and therefore it's going to have an inverse. So there's two ways now then that we just discovered to test to see if something has an inverse. You can test if it's one-to-one directly, right? We could check that out. We could talk about the horizontal line test. We could do things from that perspective. The second thing we could do is we could check to see if something is strictly increasing or strictly decreasing. How did we decide back in Calc 1 if something was increasing or decreasing? What did you do? Do you remember? Yeah, we looked at derivatives. Because derivatives would tell us what the slope's doing, right? If the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. So we could look at derivatives, and we will in a little while, to make that determination as well. We're going to start from the other perspective first, the horizontal line test perspective. So this one says, use the horizontal line test to determine if the function is one-to-one, thereby having an inverse. So again, this is not a calculus problem. This is something we can do without calculus. In fact, you can do it flat out on your calculator. That's what we're going to look at from that perspective. So grab your calculator and go ahead and type in the equation. You can clear out the ones that we had in there from before. Type in the equation 5x and then your square root of x minus 1. And take a look at the graph. What's it look like? Almost. Yeah, and so the window is probably, if you're doing that 10 by 10 window, not a very good window for this particular graph. So let's manipulate it a little bit. We can see that it's, at least by manipulating, we can see it's not a line. Everything's in quadrant 1, right? In your picture, is it? Mine is. So what I'd like to do is, in my window, I'm going to hit window. And I'm going to make my x minimum 0 and my y minimum 0, because I know I don't need the left or the bottom of the graph. So this will help some. So go ahead and graph it. It's better. It still looks awfully straight, doesn't it? What I really need is I need a higher y value to see what's happening. Agreed? So how do you get that? Well, what'd you do?
Make y 100.
You could make y just larger. But what if like 100 is not big enough, Nate? Any ideas then? 1,000, you could just keep increasing it. You can do that. There's another cool feature in your calculator. What's that? Keep using larger x values or on the larger y values, I think you mean. Oh, you could see on the table to see how large it would be. What did you suggest doing? Zoom fit. That's my favorite. So maybe you haven't seen that one before. I want to make sure you've seen some of these cool calculator features. Hit zoom. And it's actually number 0. So if you type 0 or if you arrow down to 0, what it will do is it will take the x values you already had. So if yours were like mine, it was set from 0 to 10. And it will automatically pick the y value that you need.
It's 150.
Isn't that fantastic? Was it 150?
I wasn't far off.
You weren't far off. That's pretty good. So any way you do it, your whole goal is to kind of see that this does in fact curve, but it doesn't fail being 1-to-1, right? So mine looks something like this. The reason I'm not hitting any of these axes is because I know from my original graph it didn't, right? It definitely did not actually hit down there on the bottom of the graph. And if you look at very carefully at the equation itself, the reason is because I can't have x values that are smaller than 1, right? Or I'd have a negative underneath my radical sign. So that's actually why it's not going to hit any of these axes. But this picture, clearly, we can see that this is 1-to-1, right? It passes the horizontal line test. Any horizontal line you draw crosses the graph at only one place. So this is 1-to-1. Therefore, it will have an inverse. Okay, so now we know how to decide, and we'll do the other test later. We know how to decide if it has an inverse, but we haven't talked about how to find said inverse, have we? So let's talk about that next. Actually finding the inverse. So this is a 6-step list of what you can do to find an inverse. We already did step 1, decide if it's 1-to-1. So if you fail step 1, then you're done, right? I don't mean you as a person fail, but if the function fails. If it is not 1-to-1, you do not have to keep going down the list. So figure out if it's 1-to-1. A lot of times your equations will start out saying f of x equals or g of x equals or something like that. It's a lot easier to work with it if we change the f of x just to the letter y. Step 3 is the first actual manipulation that we've done that's of consequence. We replace x with y and y with x. That's an actual real change in our graph, right? And then on step 4, we're going to solve for y, the new y that we just created, if you will. After we've solved for y, we can give y the name f inverse of x or g inverse of x or whatever it was from beginning, right? Just repeat it with that notation in the inverse. And define the domain. That matters sometimes. If the graph's domain's all real numbers, you don't usually see it defined, but if it's restricted, like it's only the x value is bigger than 7, I don't know why 7 is my favorite number today, but apparently it is. I think I've used it 3 times. So then you have to talk about that. You do have to restrict the domain if there's a need for a restriction. And then the 6th step is to verify your answer. So verifying your answer could mean a couple of different things. It could mean graphing them. Make sure that they flip over the y equal x line, right? It's a reflection. It could mean actually plugging one into the other one and making sure that you get back x when you're done. But that's what verifying your answer would be, okay? Would be checking that step. Okay, so let's try one. X cubed minus 1, and we're going to find the inverse function. So the first thing we need to do is what? Make sure it's 1 to 1. Now, this graph is one that you should be fairly familiar with. Maybe not with the minus 1 on the end per se, but the x cubed graph. You guys know what that looks like, right? Can you picture it? Yeah. So most of you are drawing like this in the air. Yeah, you're doing that? And then what does the minus 1 on the end of that graph actually do to the graph of the original? It's going to bring it down 1. Is that going to change whether it's 1 to 1? No. So if I had a plus 1 or a minus 1, either inside or outside, whether it shifted it left, right, up, and down, it's not going to actually change the graph. Now, if it said x cubed and then it had a plus an x squared or plus an x, then you got to be more careful, right? That might actually create something that does this. And that would have problems with being 1 to 1. Okay? So you don't get any of that change in direction unless you end up with a linear term or a squared term involved, and we don't have that. Okay, so the first thing, checking to make sure it's 1 to 1. Yeah, it's 1 to 1. We checked. So that was step 1. I'll label them as we go. Step 2. What does step 2 tell me I have to do? Yeah, so it's just going to say y equals x cubed minus 1. What's step 3? Switch them. So x equals y cubed minus 1. And then step 4 is to do what? Solve for y. So when I solve for y, I'm going to add the 1. And then what am I going to do to get rid of the cube? Take the cube root. So this is going to be y equals the cube root of x squared, of x plus 1. That's step 4. Step 5 is to replace the y with f inverse of x. And again, if your web assigned homework chooses that x is not x and it's t, just make sure you're using the notation they use. If this weren't f of x, it were g of x, make sure you're using g inverse for your answer at this point. It mentioned domain issues. Cube roots, if you'll remember, don't have domain issues. I can put anything underneath a cube root and get an answer out, positive, negative, or 0. There's no problems with cube roots. If this had been a square root, that statement would not be true, right? So this one doesn't have domain issues. So if you want to list that the domain is all real numbers, or if it asks you to list it, that's fine. If you leave it off on this one, that sort of makes sense because it doesn't have any issues. So the assumption is that it's all real numbers. Step 6 is to check and make sure that we have the right answer, to verify. So I'm going to suggest that we verify this with our calculator. So go ahead and take your calculator, the original equation, x cubed minus 1 and y1, and your cube root. So there's a couple ways you can do cube root. If you hit math, it's the option number 4. And that's your easiest way to do it. So let's just go with that one. And then it was supposed to be the cube root of x plus 1, right? take your window back to zoom 6. That's the standard window. And your graph should look something like that was close. I think that's pretty good. So it looks something like that, your graph. I'll draw mine up here, but if you want to, you can actually put in y3, y equal x, to actually see the line on your screen of your calculator to sort of verify it visually that it's doing this. This should look like a reflection if I put that line in there. Does it look okay? Excellent. Okay, now that actually is part B. Oh my goodness, we were getting ahead of ourselves, or at least I did. It says graph f and its inverse on the same set of axes. So that one would do it. Okay, that's one way to verify. We verified it with a graph. So there we go. It's done. Part B, just like that. All right, do you have it on there? Part B? All good. We've got the graph and its inverse. Let's go ahead and label them. The original one was up here. This was f of x. This one down here was f inverse of x. And the one in the little middle was the line y equal x. All right, I'm not going to give you the answer for part, so you're going to write it down on your own, and then we're going to make sure you write down the right thing. Describe the relationship between the graphs. In your own words, on your paper, write down what is the relationship between these graphs. What'd you guys write down? What did you say, Nate?
Since the graph f of x is 1 to 1, since the graph f of x is 1 to 1, the graph f, how you said it, inverse?
F inverse.
F inverse of x is the inverse of f of x along the line at y equals x.
Okay, so what does that mean graphically? What does it mean for it to be an inverse graphically? Right, reflection. We get a reflection over the line y equal x. So because we have that inverse relationship, we do get that reflection relationship going on with the graphs. So that's what we're wanting to hit on part C, was that reflection relationship. Okay, we already mentioned this one, but we will fill this in now. It asks for domain and range, which I didn't mention before either. The domain and range of f and its inverse. So the graph of f was this one right here, x cubed minus 1. Domain means x values. What x values are you allowed to plug into x cubed minus 1? All real numbers. And you can do that in one of two ways in terms of writing that out. So you can use interval notation, that's negative infinity to infinity. Okay? Or, if you'd like, you can use the r like this with the double lines on the left. That means all real numbers. That'd be okay as well. So that's the domain. I'm going to use this r for range. Maybe I'll write it out just to clarify it, since I used r down there. Range. Range means what y values do you get out of the graph? That's actually a harder question in terms of looking at the equation to ask, but if you think about the graph, it's not too bad. What y values do you see or could you see present along the graph of x cubed minus 1?
Isn't it also all?
It is all real numbers on this one, yes. So either negative infinity to infinity or r. Okay, no matter what y value I want to consider, I can scroll up or down on my window and it will be on the window, right, at that y value. That's for the function. It's at the function and its inverse. Now, let me tell you a trick. If you do it for the function, You've already done it for the inverse. What was the relationship when we did it with this process over here, these steps, that changed it, really, really changed it from a function to its inverse? Right, x and y switching. And x is the value for the domain, and y is the value for the range, right? So if we switch x and y, we're actually switching what? The domain and range. So it's not very helpful on this particular example for me to say that, because everything's the same. It's all negative infinity to infinity. I mean, I get it. But on other graphs, that won't be the case. When you're writing down the domain here, all you have to do is look up at what you wrote on the range for the first one. Well, that was negative infinity to infinity. And when you're looking on the range for f inverse, all you have to do is to look up at the domain for the original, and that was negative infinity to infinity. Again, or you can use the real number notation. Okay, let's take a look at one more topic in this section, continuity and differentiability. Let f be a function whose domain is an interval I. If f has an inverse function, then the following are true. If f is continuous, then f inverse is continuous. If f is increasing, then f inverse is increasing. If f is decreasing, then f inverse is decreasing. And if f is differentiable on an interval containing c, and it's not 0, then f inverse is differentiable. That's pretty friendly, right? Basically, all these important features are going to be the same for the two graphs, with a couple of sort of exceptional, things that could happen on the differentiability stuff about what happens when zeros get involved. We always have to be careful about those. Okay, I had mentioned on this last example that we were going to do this, so this is the example in which I was referencing before. We're going to use the derivative to determine if the graph is strictly monotonic and therefore has an inverse. You'll notice we do have a restriction on the domain on this one, right? The 0 to infinity on the right-hand side. Why is that necessary, do you suppose, for this graph?
Is it x squared on bottom?
Yeah, x squared on bottom, and when we square x, we get graphs that have some symmetry involved. So this one won't be parabola because the x squared is in the denominator, but we still get some sort of symmetry where we get the same y value coming out whether you put x as positive or negatives in. So we're restricting our equation to talk about only the values for x as positive. Now the question asks us to use the derivative to determine that. So this is going back to that earlier theorem definition, I can't remember which one it was, that we said that if it's strictly monotonic, it's going to be 1 to 1, and if it's 1 to 1, then it has an inverse, right? So we're trying to decide if it's strictly monotonic using the derivative. So the first thing we're going to do is we're going to take the derivative. All right, so one of the things that you might remember before you take the derivative is that this will be easier to take the derivative of if I rewrite it like that. Because otherwise I have to use a quotient rule, and it's just awkward because I've got a constant on top. So it's just an awkward way to do it. And this one's also faster, and that in and of itself makes it nice. So what's the derivative of 4x to the negative 2? Right, negative 8x to the negative 3. And so this is negative 8 over x cubed, right? So far, so good? Okay, we took the derivative. So again, what does it mean to decide if it's strictly monotonic? That is, if it's strictly increasing or strictly decreasing. Well, it means that what we want is we don't want there to be any change in value. We want it to be always positive or always negative, the derivative, that is. So we need to see if this thing ever does actually change from positive to negative or negative to positive. So how do we do that? Well, we kind of test it to see, is it ever equal to 0? Because if it equals 0, it might change from positive to negative or negative to positive. So what can you tell me about this graph? Does the function does the function's derivative ever equal 0? No. Why not?
Because you can't get a negative, well, you can get a negative future, but that would
I think it might be even easier to think about a different way, actually.
You can't divide by 0.
Well, we can't divide by anything and get 0, actually, right? There's no number that I can divide -8 by and get 0. Somewhere along the way, probably somebody told you that in order to get a fraction to equal 0, the numerator has to be 0, right? What do you know about this numerator? It's negative. It's not 0, right? It's not possible because there's no variable in the numerator. It's a constant. So this can't ever equal 0. So whatever this graph is doing, it's doing it constantly unless there's a change where there's an asymptote. Is there an asymptote in this graph? There is. Where would there be a vertical asymptote in this graph? Yeah, at x equals 0, right? Because 0 would make the denominators, x equals 0 would make the denominator 0. So we do have an asymptote in this graph. So there's two places where a graph can change from increasing to decreasing. They can change if they equal 0, the derivative equals 0, or it can change if the derivative does not exist. And this one does not exist at x equals 0. But there's something in the back of your mind that should be saying that's okay. Our domain is restricted. I don't have to worry about what happens when it's less than 0. I only care about one side of this thing when it's greater than 0. So it doesn't end up mattering. So the f prime of x does not equal 0, and it does not exist. It is D and E when x is equal to 0, right? This is what we just said. But our domain is 0 to infinity. Okay? So which is this? Is this strictly decreasing or is it strictly increasing? It's decreasing. How do you know? The derivative is negative. F prime of x is less than 0, or it's negative if you prefer, on the domain 0 to infinity. If you plug in any value bigger than 0 into the derivative, you'll get a negative on top and a positive on bottom. And a negative divided by a positive is a negative. So this was strictly, well, it's written, let me write it down. Therefore, f of x is strictly decreasing and therefore has an inverse on the domain, on 0 to infinity. If this did not have the restriction 0 to infinity, would it have an inverse? No, it wouldn't. And if you want to, real quick, just for fun, go ahead and grab your calculator and plug in 4 over x squared. I think your standard window will be sufficient for looking at that. Oh, yes, it is. Do you guys see it? Yeah, this definitely, if you look at the whole graph, right? That is from negative infinity to infinity, it definitely duplicates all those y values, does not pass that horizontal line test. But if you restrict your viewing to only the right-hand side of the graph, you're okay. Okay? And this is using calculus to make that same determination that algebra confirms for us as well.